Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. We know intuitively that if we are around loud sounds, they might mask us from hearing quieter sounds. In this video, we'll learn more about this masking phenomena and how it is manifest in what we think we hear.
So let's get started. The field of psychoacoustics seeks to quantitatively correlate acoustic stimuli and hearing sensations, and the first psychoacoustic phenomena that we'll study is the fact that loud sounds can hide quieter sounds.
I'm gonna make this quick. I came here for you. When I get on with my life, I want you with me.
You're a thief.
You lied about being a thief. You don't do that anymore.
Steal.
Lie.
We know this intuitively, and this is termed masking. It's very influential in our day-to-day lives. For instance, we might be approaching the sink full of dirty dishes and still hear a neighbor ask us if we'd like coffee. But if we were washing dishes, that message of "would you like some coffee" could be blurred and obscured in the background. Understanding the factors that influence masking can help us appreciate the limitations of our hearing as well as where we have strengths. So consider first a 550 Hertz tone. This will beep. There'll be some background noises with it as well. Let's try a 1000 Hertz background noise. And now let's use a 500 Hertz background noise. And what about a 250 Hertz background noise? Well, we find that we struggle to hear the 550 Hertz tone as the masking background noise has a frequency that's slightly less than the tone, but not too low. As a result, when the tone and masker are more distant in frequency, we can still differentiate the 550 Hertz beep. So why does this trend occur? It occurs due to the mechanism of wave travel through the basilar membrane in our cochlea. The lower the frequency, the further along the basilar membrane that the acoustic wave propagates. The lower frequency also causes greater displacement excitation of the basilar membrane. In other words, sounds are masked because the basilar membrane is excited on neighboring regions. And lower frequency masking is more substantial and effective due to the fact that the lower frequency waves more highly excite the basilar membrane, creating a difficult time for us to differentiate what tone is present in the sounds we hear. Noise can also mask tones. Listen and see if you can hear the moving tones within the 1 kHz band-limited noise that's 60 decibels in level. What we find is that for band-limited noise, the test tone level must be louder than the noise to be heard for tones that are near to the noise band center. In other words, for the 1 kHz test tone, the approximate level of the test tone needed to be heard is greater than the 60 decibels of the background band-limited noise. To summarize what we have learned, Masking is the phenomena of sounds interfering from our ability to hear what we want to hear. Masking occurs due to overlap of the excitation on the basilar membrane, making it difficult to distinguish the cochlear signaling from one sound to the other. Masking is also more prominent for noises that are slightly less in frequency than the test tone. This is explained by the traveling wave behavior of lower frequency waves along the cochlea.
That's it for this video. In the next video, we'll learn how masking and other psychoacoustic phenomena impact our hearing sense and therefore influence what we think we hear as sound.